Good morning, Year 12 further mathematicians. Just going to start off with 11.7, the next subchapter in chapter 11. It's to do with partial fractions and integrating functions using partial fractions. Now, partial fractions we've actually done before. That was chapter 1 of this Year 2 book. There are a few different types of partial fractions, so you might need to go back and revise partial fractions because I'm going to assume that you have remembered it. But 11.7, we're going to use partial fractions to help integrate certain functions. So, first function we have to integrate is that one. Integrate x minus 5 over x plus 1, x minus 2 with respect to x. There's no other way to integrate this apart from using partial fractions. The fraction itself, if you've done partial fractions, will look familiar. We've got this type 1, and there's a certain way we have to split this up into partial fractions. So I'm going to focus on the thing we are integrating, which is x minus 5 over x plus 1, x minus 2. And you need to be aware that the partial fractions for this looks like the following. This splits up into x plus 1 and something over x minus 2. And the values of a and b are something we need to find out. And that's a type 1 partial fraction. And to find out these a's and b's, there's lots of ways of doing it. The best way to do it is to actually simplify and write the right-hand side as a single fraction. So that would be equivalent to a brackets x minus 2 plus b brackets x plus 1 all over x plus 1, x minus 2. And then you've compared both sides, and you can effectively forget about the denominators. X minus 5 over x plus 1, x minus 2. Forget about the denominators, and just the numerators need to be correct. So cancel those off, and you've got x minus 5 needs to be identical to a x minus 2 plus b x plus 1. And now there's a few options on how to work out these a and b values. There's something called comparing coefficients, or making use of the fact this is an identity. It would have to work for every single x value. So if you pick certain x values, you can generate some equations and then solve those equations. So the best x values to pick in this case would be x is 2, and also x is equal to negative 1. And let's see what happens if I substitute 2 into this identity. We'd get 2 take away 5, which is negative 3, and that would have to be equal to, put 2 into this, that goes to 0, put 2 into this, that goes to 3b, to give you b is equal to negative 1. Next one, put minus 1 in, put minus 1 into this, you get minus 6 is equal to, now this second term now would go to 0, and you're just left with minus 3a to give you a is equal to 2. So in other words, that partial fractions thing at the start would be the same as 2 over x plus 1 minus 1 over x minus 2. And now we want to integrate this instead. Partial fractions will allow us to rewrite that original thing into something we can integrate. Because if I integrate this with respect to x, that's equivalent of integrating both of these separately. And you should know how to integrate these. First one would go to 2 ln x plus 1. Second one would go to minus ln x minus 2. And remember the plus c. You can leave your answer like that, because that's all you're asked to do to integrate. If you had to write this as a single logarithm, then you'd have to use some log rules. For example, this is extra stuff now. This is equal to ln x plus 1 squared minus ln x minus 2 plus c, and finally ln x plus 1 squared over x minus 2 plus c. But you get all the credit for getting that far. And that'll be it for EG number 1. I'm going to pick on an EG number 2, which is a different type of partial fraction. We've got this function. I'm going to integrate 8x squared subtract 19x plus 1 over 2x plus 1 x minus 2 squared. And we approach this exactly the same way. Now in an exam, they might actually give us a clue as a part A, take that fraction and write it in partial fractions and then say hence integrate. It's not guaranteed though, but obviously because this is in the partial fraction subchapter, we're going to have to use partial fractions at some point. So we're going to take 8x squared minus 19x plus 1 over 2x plus 1 x minus 2 squared, and then use our knowledge from chapter 1 in the textbook. Think about what type of partial fraction this is, and if you look back in the textbook, this should split up into a over 2x plus 1 plus b over x minus 2 plus c over x minus 2 squared. When you've got a repeated root or repeated bracket on the denominator, you get both the squared one and it by itself. Then you're going to try and simplify the right hand side like we did last time. This is equivalent to a x minus 2 squared plus b 2x plus 1 x minus 2 plus c 2x plus 1, and then 8x squared minus 19x plus 1. All of those are over the same denominator now, which is what we needed. 2x plus 1 x minus 2 squared, and 2x plus 1 x minus 2 squared. When you've got them over the same denominator, cancel the denominators, and then you've just got the numerators equal to each other. And again, there's many ways to do this. You could use something called comparing coefficients, but that would actually end up requiring you to work out or solve 3 equations with 3 unknowns. But if we use a similar method to the one I did in EG number 1, pick specific x values using the fact that it's identical, then this isn't so bad. So good x value to pick would be x is equal to 2. If you replace every single x value with 2, this term disappears, this term disappears, and you're only left with the third term. So what would that be equal to? So 2 times 2 plus 1 is 5, so 5c. I'm going to use my calculator to work out the other parts. So 8 2 squared subtract 19 2s plus 1 gives you negative 5. So minus 5 is equal to 5c, to give you c is negative 1. Right, keep going. Another good x value to pick would be x is negative a half. If you substitute that in, 8 negative a half squareds subtract 19 negative a halves plus 1 is equal to, this time the second 2 terms disappear. That goes to 0. that goes to 0, and you're only left with this, which is, not going to rush this actually, so a brackets minus a half minus 2 squared. Okay, if we simplify the left hand side, minus 0.5 squared, subtract 19 minus 0.5s plus 1, 25 over 2 is equal to minus 0.5 minus 2 squared, 25 over 4, a, and if you make a the subject, you get a is equal to 2 for that one. So that's 2 of the unknowns worked out. Got one more to work out, but there's no good x values to pick or something that's going to make this really easy. So you get to pick any x value. The one I would always use if I hadn't used it yet would be x is 0. So put 0 in, replace every single x value with 0. At least the left hand side simplifies quite a bit. You get 1 is equal to 0 into this, you get a 4a. 0 into this, you'd get minus 2b. 0 into that, you get plus c. And we want to make b the subject effectively, so 2b is equal to 4a plus c subtract 1 to give you b is equal to, well, if we replace now the letter a with the number 2 and the letter c with negative 1, so 4 times 2 plus minus 1 subtract 1 all divided by 2, and what would that give you? That would be 8, 6 on the top, so 3b would be 3. And in other words, that original fraction now in partial fractions would be 2 over 2x plus 1 plus 3 over x minus 2 plus c, which was minus 1, so minus 1 over x minus 2 squared, and we are integrating these with respect to x. Okay, let's do them all separately. So we're going to integrate 2 over 2x plus 1 with respect to x. We're going to integrate 3 over x minus 2 with respect to x. And we're going to integrate 1 over x minus 2 all squared. Now, some of these are going to be lunds, but this last term is not going to be a lun. Okay? This one has the bracket squared on the denominator, and if I haven't got all of the others like brackets to the power of 1, and they kind of indicate lunds, but this one would be something else. So the correct way to do this is actually write it in index form. Now I don't want to get these wrong, so I'm going to actually make some guesses and see how bad these guesses are. So for this one, I'm going to guess ln of the denominator. So if I said y is equal to ln 2x plus 1 and differentiated to see how bad the guess was, it'd go 1 over 2x plus 1. But by the chain rule, you'd have to times by that bracket differentiated, so times by 2, which gives you 2 over 2x plus 1, which is actually perfect. So it was a good guess. This one, guess ln in the denominator. Do dy by dx. 1 over x minus 2, and this time you are times in by 1, because that bracket differentiated goes to 1. So that's 1 over x minus 2. I wanted 3 over x minus 2, so I just got to remember to times that by 3. And the last one, something to the power of minus 2, your guess should be add 1 to the power. So x minus 2 to the power of minus 1. And then dy by dx would be equal to something to the power of minus 1 using the chain rule is bring the power down, knock 1 off the power, and then times by that bracket differentiated, so you just times it by 1. So this gives you minus x minus 2 to the power of minus 2, which is like a minus sign out, unfortunately. So I'll just have to times my answer by minus 1. So then let's put those all together. So the integral, which I'll call I, would be equal to, that guess was perfect, so I can keep that, ln 2x plus 1. This guess was out by a factor of 3, so I will times that by 3. This time I'm subtracting, and this guess was out by a factor of minus 1. So you're actually minus in a minus, so minus x minus 2 to the power of minus 1, and then that would be a plus in the end. And remember the plus c is job done for that. So this is partial fractions. You will have to know the different types of partial fractions. So if you have to revise that, that's chapter 1. You guys are going to practice some questions from the textbook. So if I direct you to page 312, exercise 11G. I would like you to do question 1. Actually, no, let's do question 3 and question 4. Just going to do 2 questions today. Unless I can think of another one. Question 2, question 4. Actually, why not question 6 as well? Question 6. Give you a clue on question 6. Remember to factorize. That'll be it. Thank you very much, and I'll speak to you soon.